In this lab report, we will explore the principle that is known as Ampere's principle, which capitalizes on the fundamentals of electromagnetism. To understand what Ampere's law is, it is the magnitude of the magnetic field in the space around it when it is produced by an electric current. This is achieved simply by utilizing copper wires in a series of turns, which will amplify and produce a magnetic field. Fun fact, it is through this principle that we can understand how powerful the electromagnetism is in MRI machines. Essentially, these machines are solenoids that are constructed on a greater scale to permit visualization of activation in a myriad parts of the brain. To further understand the applications and basic empirical principle, we will utilize copper coils with a differing series of turns, also known as our solenoids. Here we will assess if the number of turns has an impact on the magnetic field that is produced when current is applied to them. Foundationally, when we look at the current and magnetic field relationship, this can be easily depicted by using your right hand as a guide, by making a thumbs up position, and your thumb will represent the direction of the current, while the rest of your fingers will serve as the direction of the magnetic field. Now that we have established what is Ampere's law, its real-life applications, and as well as the basic principles that build up on this phenomenon, we can now dive further into the empirical experiment on understanding how differing the number of coils of solenoids can impact the magnitude of the magnetic field.
For this experiment, we used a small set of tools that let us create and measure magnetic field inside of different coils. And for this experiment, we were allowed to design our procedure. And the first piece of equipment was the power supply, and this is what provides the current for our circuit and allows us to adjust exactly how much current flows through the coil. Since Ampere's law tells us that the magnetic field depends on the current, this device is needed. Next, we use the Pasco interface, and this box is connected to the computer that reads a signal from our magnetic field sensor, and it sends all the data to Capstone so we can record and graph our measurements accurately. Then the magnetic field sensor is the long black sensor that you see on the table, and we insert that into the center of each coil to measure the magnetic field produced when current flows. And this is the main measuring tool in the experiment. We also use several coils with different numbers of turns, and each coil has a label showing how many loops of wire it has. They range from about 200 to 1600. And these coils are important because our goal is to see how the magnetic field changes when the number of turns is doubled. So more turns means the magnetic field should add up more strongly. And we had a retort stand that and a clamp that were used to hold the coil steady so the sensor could be placed in the same position every time. And we use a connecting wire to complete the circuit between the power supply, coil, and interface. So together, all these materials allowed us to create a controlled setup to test the relationship between the current number of turns and magnetic field strength.
For the procedures, our goal to the experiment was to measure the magnetic field within a coil with 3 different trials doubling. To successfully do so, the following steps were taken. We first turned on Capstone to record the magnetic field data, then turned on the voltage machine, and then connected a magnetic sensor to interface in order to collect the data. For trial 1, we placed a coil of 200 in a holder. We then ran the voltage and recorded data. For each trial, we did use different voltages. For trial 2, we then placed a coil of 400 in the holder, and we ran the voltage and recorded the data. For trial 3, we placed the coil of 800 in the holder and recorded the data from all the trials. In order to successfully get the proper results, we were able to do everything correctly.
Okay, so on this slide, I'm showing the data we used for the experiment. The whole point of what we were testing was how the magnetic field inside a coil changes when you change the number of turns in that coil. The coils we used were labeled 200 turns, 400 turns, and 800 turns. That just means how many times the wire is wrapped around the coil, and it's just the number of loops of wire. We kept everything else basically the same for all 3 coils. The current coming from the power supply was about 1.5 amps, and all the coils were the same size and same length. So the only thing we were intentionally changing was the number of turns, and that makes it easier to see how that one variable affects the magnetic field. Now looking at the number in the table, the 200 coil gave a magnetic field of about 1.88 millitesla. When we switched to the 400 turn coil, the magnetic field went up to 3.77 millitesla, and with the 800 turn coil, it jumped all the way to 7.54 millitesla. And this gives us a basic pattern. So every time we doubled the number of turns, the magnetic field basically doubled too. And that's essentially the big takeaway from this experiment or this slide. So overall, this slide is just laying out the data that we were working with, and it shows that the coils with more turn produce stronger magnetic fields. Moving on to data analysis. So now I'm going to break down what our data actually means and how it connects to the physics behind this experiment. The main idea we were testing is something we learned in class. The inside of a coil of wire, the magnetic field depends on how many turns the coil has. If you keep the current the same and the coil length the same, then adding more turns should make the magnetic field stronger. That's the basic prediction from the theory. Now looking back at the numbers we got, everything lines up really well with the idea. With the 200 turn coil, the magnetic field was about 1.88 millitesla, and when we switched to the 400 turn coil, that number basically doubled to 3.77 millitesla, and when we went all the way to 800 turns, the field doubled again to around 7.54 millitesla. So the pattern is pretty clear, and every time the number of turns doubled, the magnetic field doubled too, and that's exactly what the theory says should happen, which shows that it's not random and it increases at an interval. So the big takeaway from this slide is simple. Our results support the idea that the magnetic field inside a coil increases in direct proportion to the number of turns, and the theory predicts it, and the numbers we calculated show the same behavior. So to wrap everything up, our final lab was really about testing the relationship between the magnetic field inside a coil and the number of turns that coil has. The whole point was to see whether the theory we learned in class actually showed in a hands-on setup. Using real equipment, we ran 3 different trials using 3 different coils, one with 200 turns, one with 400 turns, and one with 800 turns, which basically gave us 3 levels of comparison to see how the magnetic field changed. Even though we didn't use a graph in the presentation, the values we got made the pattern really clear. As we increased the number of turns, the magnetic field increased in a really predictable way, and when we doubled the turns, the magnetic field basically doubled too. That's exactly what the theory says should happen, so seeing the data match that so cleanly helped confirm that our setup was working the way it was supposed to. It also reinforced that the relationship between the magnetic field B and the number of turns N is proportional as long as everything else stays the same. What our result showed is that every turn of wire in the coil contributes to the total magnetic field inside the coil's core. The more loops you add, the stronger the magnetic field gets. This idea comes straight from Ampere's law and the formula for a solenoid, which tells us that the magnetic field depends on the number of turns, the current, and the length of the coil. Since we kept the current and the length the same for all 3 trials, the only thing affecting the magnetic field was the number of turns. And that made the effect really easy to see, and our data basically verified that design. All 3 coils behaved the way the theory predicted, and the increases in the magnetic field allow the exact pattern we expected. So overall, the experiment did exactly what it was meant to do. It helped us prove that the magnetic field inside a coil is directly influenced by how many turns of wire it has. It also showed how the structure and design of the solenoid play a major role in determining the field strength. Even though this is a simple setup, it does a great job of connecting the theory from class to real world measurement. and it helped us understand how magnetic fields behave in a practical and observable way. So, in conclusion, our lab didn't just show a pattern, it actually supported the physics behind that pattern, and the number of turns and the magnetic field had a clear and consistent relationship. And the experiment helped us see Ampere's law in action.